Good morning, one and all. So, we are going to start a new topic that is our unit 3 of our syllabus, and it's called Sequential Logic Design. Sequential Logic Design. In some of the books, they can also write SLC, Sequential Logic Circuits. Okay, in some of the books, they will write Sequential Logic Design SLD or SLC. Okay, so in this first question would be a very important question. What is the difference between the combinational logic design and sequential logic design? What is the difference between CLD, combinational logic design, and SLD? Okay, so in this case, what we have to do, we have already discussed much about this combinational logic design. So combinational logic design is nothing else. The output is only depending upon the present input of the circuit. Okay, so the output of the circuit, so this is the combinational logic design circuit. The output of the circuit only depends upon the present input. Okay, if present input getting changed, the output is also getting changed. So output is a function of present input. This input is here, nothing else, the present input. It doesn't depends upon the past output or past input or whatever may be. If this input at this present time at t equals 0, if it changes, then obviously it will be reflected at the output. So what are the examples of this combinational logic design? The examples will be here. We have already done arithmetic circuits. Okay, arithmetic circuits in the set adder, subtractor, half adder, full adder, like many circuits. Then we have code converters. Okay, code converters. Next, MOX, multiplexer. Next, DMOX. We have seen all these things. Next, decoder. Next, encoder. These are many circuits. These are all called combinational logic circuits. Why? Because his present input is getting changed, the output is getting affected. Okay. Now we'll move to the sequential logic design. So in case of sequential logic design, the output of the logic circuit not only depends upon the present input but also the past output. Okay, so the output of this circuit, so this is CLD. So what will happen here? Mainly the past output is here. The past output is also getting feedback to the input side. Okay, so this complete circuit now, CLD plus the past output, is known as SLD, sequential logic design. So this past output need to be stored in some place. Okay, whenever it required, it's going to be feedback to the input side. So in order to store this past output, we will have a memory element. Okay, it will actually store the past output. So it is having CLD. Next, this is output, present output. This is my present input, and the past output will be feedback through the memory element. The memory element will hold the past output and it will feedback to the input side. Okay, so this is combination. This is called sequential logic design. This memory element actually stores the previous output. Okay, previous output. So now output of the sequential logic design is not only depends upon the present input but also the past output. This output is nothing else your past output or previous output. Okay, this is your present input. This is your present input. All of you understand, this is your present output. So present output of the logic design not only depends upon the present input but also the past output. This past output is stored in this memory element. Whenever required, is going to be feedback there. So what is the difference between combinational logic design and sequential logic design? Mainly there is no feedback path, so it only depends upon the present input. But here output of the sequential logic circuit depends upon the present input as well as the past output. The past output will be feedback through the memory element. The previous output is stored in the memory element. So there is a feedback path in sequential logic design and there is no feedback path in the combinational logic design. So now the examples of the combinational sequential logic design are flip-flop. We'll discuss all these things: counter, registers, shift registers. Okay, next many things are there. Okay, these are the main examples of this sequential logic design. So now the thing is, we have already studied this part. Am I correct, students? Combinational logic design, we have already studied this. If we can know about how to design memory element, then we can already cover up this SLD. Am I correct? We have already studied about this CLD. Now, if we can able to understand what is memory element, how it works, and how it stores the previous output, how it stores my desired value, how it actually feedback to the combination logic design, how what is the procedure to feedback. If we know all these things, then we can cover up this SLD. So without wasting time, I will directly start with the memory element. Understand? Everybody understands, students, what is memory element now? Memory element is nothing else. It is going to store the data. Okay. What is the data? Binary data. Okay. So I'm just going to tell you here a basic memory element. Just see here how I am designing. So I'm just getting a, okay. So what I have done, students, I know this is my NAND gate. It is a combinational logic design, and I have taken feedback from the output. Okay. So this is my A, B, let's say, and this is my Q and Q bar, let's say. Okay. And I'll tell you all these things. Don't worry. In case of memory element, remember one very important concept I am discussing here. Okay, what is that? A memory element contains always two outputs. What are those outputs? One is called true form of output, it is Q, and another one is complement form of the output, Q bar. So if Q is 0, Q bar is 1. If Q bar is 0, Q is 1. They both of them are complement to each other. So this is one first very important concept. What is that? A memory element contains two outputs. Next, these two outputs are complement to each other. You know. Okay. Next, the output of memory element generally represented with variable Q and complement of the variable Q bar. Okay. And another assumption is always memory element has some initial assumption. Let's say initial assumption I am having this is here 0 and here 1. Okay. So these are the 4 points you need to assume first before analyzing any memory element. Okay. First one is what? A memory element contains two outputs. These two outputs are complement to each other. Complement generally represented with Q and Q bar. Next, we would have initial assumption to Q is equal to 0. Let's say Q bar equal to 1. Your wish. You can also do Q equal to 1, Q bar equal to 0. Your wish. Okay. So these are the initial assumptions while going for the any analysis of the memory element. Now, what I am going to show you here, just check it. So I have assumed here this is Q equal to 0, Q bar equal to 1. So what I am going to do with this, how we can say that this is a memory element? If this logic circuit, can I say that this is a logic circuit? Yes. If this logic circuit retains a binary digit, okay, if it retains a binary digit, then can I say that this is a one bit memory element? Okay, if it retains this binary digit, what is that retaining policy here? Retaining means, see here, I am assuming 0 here. After some time also it is actually retaining that particular value. Okay, in the next state also, let's say it retaining the same value 0, then I can say that this logic circuit is retaining a binary digit, that is 0. Okay, do you all understand, students? So what I am saying over here, if I can able to show with the help of this digital logic circuit that my output is retaining a particular binary value, that is 0 for particular amount of time, then I can say that this is called a basic memory element. Do you all agree with me? Now you can see how it is written. I am doing some analysis. Please try to understand. If you are not understanding, it's very difficult for you to next things to understand. Okay. So now you see here Q equal to 0. I have started Q equal to 0. When my Q equal to 0. If Q equal to 0, this Q is feedback to B. Can I say that if Q equal to 0, B is also 0? Okay. If B equal to 0, what is this gate, students? This is a single input NAND gate. So if it is single input NAND gate, can I say that This NAND gate is nothing else, might behave like a NOT gate. Okay, if I give it here 0, it will give me 1. If I give it here 1, it will give me 0. Do you all understand? So now if B equals 0, I can have Q bar equal to 1. Now this Q bar is feedback to A. So can I say that A equal to 1? Yes. If A equal to 1, this is again a NOT gate. If A equal to 1, Q equal to 0. Are you understanding? So what happened here? Q equal to 0. So is it retaining over here? This binary digit 0 is retaining over here? Yes, obviously it is retaining. I have proved it with the help of analysis. Okay. Now let's say somebody will tell, sir, can I take when Q bar equal to 1? Yes, you can take. If Q bar equal to 1, this will feed back to A. So A equal to 1. If A equal to 1, this is a NOT gate. So Q equal to 0. If Q equal 0, this Q is feedback to B. So B equals 0. If B equals 0, this is a NOT gate. So Q bar is 1. So are you seeing it's retaining my binary digit? Okay. So this logic circuit is called basic memory element as it retaining my binary value 0 or 1. Okay. Do you all understand? Now the question is, sir, this is only retaining 1 bit. Okay. Sir, if I want 20 bits to retain, how it will be done? Okay, what you will do, you design such circuits and make a block like this and connect it in series. So it will store 1 bit. Next 20 this type of circuit will store your 20 all bits. Are you all understanding? So what do you understand from here? You understand that for n bit memory element, are you understanding? For n bit memory element, n such circuits are required. Okay, and such circuits are required. Very, very important, students. If you did not understand, you will not understand further. I am saying, if you did not understand, tell me, are you understanding how this binary value get retained over here? Okay, with this logic circuit. So this is called binary memory element. Okay, now the thing is, here I am able to only retain the binary value. Okay, but can I able to retain it or our desired value? So tell me, what would be my desired value, students? So what would be my desired value? My desired value may be 0, my desired value may be 1, my desired value may be the previous value, whatever it is. Okay, so for that case, what I need to do? Okay, so I have to do certain modification in my circuit so that my desired values will be going to be stored in this memory element. What would be my desired value? My desired value, the previous value or previous output. It may be 0, it may be don't care, it may be high impedance, it may be 1, or it may be 0 or it may be 1. So these are my desired values. Am I correct? So can this memory element store these my desired values? Because I don't know, it may be anything will come in the previous output, because I am going to store my previous output to feedback to the input side. So in order to store this desired value, I need to have some modification to the static circuit. What is that modification? See here. So what is the next part? Modification to store a binary value. That binary value is nothing else, my desired value. So what is my desired value here? Let's say I want to store binary value 0 for 20 nanosecond of time. After that, I want to store it for 40 nanosecond of time 1. If I want to store again 1 after 60 nanosecond of time. So this is my desire now. My desire is to store 0 for 20 nanosecond, 1 for next 40 nanosecond, 1 again 1 for next 60 nanosecond. So these are my desired values. So this, what I will do, this particular memory element, it is going to store my desired value. Please check here. What I am doing actually? What modifications I am doing? So I am doing modification to the above circuit diagram like this. So if you understand this, then it is very easy for you unit 3. Otherwise, it's very tough for you students. So how I am modifying, just see. Let's say this is my A, this is my B. I have already told you what are the assumptions you have to do. It is a memory element. Your it has always memory element has outputs. These two outputs are complement to each other, and the output of the memory element generally represented by q and q bar. And there would be certain assumption at initially. Let's say I am assuming here 0, this is 1. Okay, these are the assumptions you need to write. What are those called? Those are actually called fundamental assumptions. All of you understand? So what is my fundamental assumptions? My fundamental assumptions are a memory element has two output, that these two outputs are complement to each other. Next, the output of memory element generally represented with q and q bar. Next, we would have initial assumption for q equal 0, q bar equal 1. If somebody will tell that, no sir, I will not go for q equal 0, I will go for q equal to 1. Yes, your wish, you can go it. Okay, but there will be certain fundamental assumptions you have to do. Okay, next, what is my actually requirement, students? Before starting that, I want to more discuss about little bit more about the NAND gate. So all of you know that what is NAND gate. So this is my NAND gate, am I correct? This, let's say x y, this is my xy bar. If you understand with this, it's very easy for you to analyze this circuit. So what is my truth table of NAND gate? xy xy bar. Okay, so it has 0 0 0 1 1 0 1 1. Okay, so now 0 0 it is 1, 0 1 1, 1 0 1, 1 1 0. Okay, so what I'm saying here, for NAND gate, you can observe one very peculiar things. If any of the input is 0, if any of the input is 0, then my output is 1. Okay, if any of the input of NAND gate is 0, then what is my output? My output is 1. Okay, you can see over here, if any of the input is 0, my output is 1. Okay, now if both the inputs are 1, both the inputs are 1, then what is my output? 0. Are you seeing? Okay, next, last takeaway point. If any of the input is 1, then what is that case? Output depending upon the depends upon the another input. Am I correct, students? So you can see, if any one of the input is 1, it depends upon either next input is 0 or 1. If next input is 0, it is 1. If next input is 1, then it is 0. So these are the three important concepts you need to understand about the NAND gate. Okay. So what I have told, NAND gate, if any of the input is 0, output is 1. If both the inputs are 1, output is 0. If any of the input is 1, then output depends upon the another input. Okay. So next, we'll do certain analysis now. What is analysis? What I have to do? I want to show you whether this particular circuit is storing my desired value or not. Okay, what are my desired value? My desired values are either 0 or 1 or previous value. Am I correct, students? So this is two inputs, A, B are two inputs. So how many possible combinations will be there? It has four cases will come up. Either it has 0 0, either it has 0 1, either it has 1 0, either it is 1 1. So these are the four particular cases I need to study for this particular logic circuit. Okay, and I need to see how is it behaving in the next state. Okay, how is it behaving? I have initial state, it will be q is 0, q r is 1. After the next state, how is it behaving, what it is getting? Let's say my case 1, I'm taking the case 1. What is my case 1? Let's say when a is 0 and b is 0. Okay, so if a is 0, b is 0, so at that time what is happening? Okay, so as I told you, this is what actually, this is nothing else my not get. So if this is 0, this will be my 1. If this is 0, this will be my 1. Okay, do you all understand? Now you can see I have assumed here my q bar is 1. So q bar is 1 means it feedback to this input. So if q bar equal to 1, this 1 1 will give me 0. As we know that if both the inputs of the NAND gate is 1, then I am having output is 0. Now this 0 will feedback to here. So 0 and 1 will be what? Output is 1. So what do you understand from this? Initially we have assumed 0 1. Please try to understand. Very important point I am telling over here. Initially I have assumed here my output of this logic circuit is 0 1, and after analysis I have got again 0 and 1. So what do you understand here? It's just retaining the previous value. Understand? So if A, B, 0 0, what is my Q and Q bar? Q and Q bar retains the previous value. So do you all understand, students? This is the takeaway point of this case one. Okay. What I have told you, if I can give my input to A and B 0 0, whatever may be my previous value, that is going to be retained for the next state. Okay. That is the takeaway point. Now we'll go for the next case 2. Okay. So next is case 2. So as I told you, I want my desired values to be stored by this memory element. So my desired values are what? Previous value, 0 and 1. Okay. So I have already shown how previous value is stored in this particular logic circuit. Okay. With the case 1. If I'll give A equals 0, B equals 0, then I can able to retain my previous value in this particular output. Okay. Now we'll go for the next case, case 2. What is case 2? When A equal to 0, B equal to 1. So again I am drawing the circuit for your better understandability. So this circuit is very important, students. Many times I am going to use this circuit actually. Q, Q bar, A, B, assume initial assumption 0, 1. Okay. So now see here what I am doing. So I have assumed here my I have next case I have determined here A is 0, B is 1. If A equals 0, this is just a not get. It will make output 1. If 1, this will be 0. Now this Q bar is 1. Q bar is feedback to here. This is 1. So this will be also 1. 1 1 output is what? My next state output is 0. Okay. Now this 0 is feedback to here. 0 0 output is 1. So what do you understand from this? We understand from this that if A, B, 0 and 1, it actually get Q equal to 0, Q bar equal to 1. What is the meaning of it? Q equal to 0 means what? It just reset my output, reset state of the flip-flop, reset state of the memory element. Whatever maybe previously it has, it will just reset to 0. Are you all understanding, students, or any doubt? Please let me know. Reset means it will make the output 0. Okay. So this is my case number 2. Now, so my desired value 0, I can able to store it if I can give A equal to 0 and B equal to 1 to this particular logic circuit. Okay. Now case number 3. If you are not understanding, ask me, students. When A equal to 1, B equal to 0. So at this time, what I will get? So see here, again I am doing the same circuit. So this is my Q bar, A, B, okay. And initially I am assuming here 0 and 1. Okay. Now what I have done? A equal to 1, B equal to 0. See, if A equal to 1, this will be 0. If B equal to 0, this will be 1. Okay. Now what I have done? 0, sorry, 1 is actually feedback to here. So this is 0 and 1. What? 1. Next state will be 1. Now 1 is getting feedback to here. So 1 and 1 is 0. So what is happening here? Initially I have 0 1. Now it makes my Q to 1. So what is happening here? If A, Q and Q bar. So if A, B 1 and 0, it just make my Q to 1. So this is called set. It's just setting my output. Okay. This is called set state of the memory element. Okay. Do you all understand all three cases? So what do you understand from here? With the help of A, B 0 1, my desired value to be stored is 0. If a equal to 1, b equal to 0, my desired value to be stored in this logic circuit is 1. This 0 is called reset of the flip-flop. This 1 is called set of the flip-flop. Okay, these three cases actually gives me all my desired values. What are my desired values actually to be stored so that I have done such a modification? My desired values are mainly previous value, either 0 or 1. These are the three things. I have already got this thing. Okay, now the thing is, you should have in your mind, sir, if I'll give a equal to 1, b equal to 1, what will happen? Obviously, that is my case 4 I am going to discuss here. So how it will actually behave if I'll give case q equal to sorry, a equal to 0, a equal to 1, and b equal to 1. Just see over here. Next case number 4. Oh my god. Okay, so my next case is case number 4. So in this case number 4, what I'm doing is I'm taking the same logic circuit. Okay, and I have taken here A, B, this is my Q bar. Taking fundamental assumption here, my Q equal to 0, Q bar equal to 1. Now I have taken A equal to 1, B equal to 1. So if A equal to 1, it will be 0. If B equal to 1, it will be 0. Now you can see Q bar, this fed back to here. So this will be 1, 0 and 1. What I got here? If 0 and 1, it is 1. Now this 1 will feed back here, 0 and 1, I got 1. So is it possible Q and Q bar both will be 1? No. Okay, anytime, because Q and Q bar both are complement to each other. If Q equal to 1, Q bar must has to come 0. But here in this case 4, when I have applied A and B equal to 1, I have got one peculiar thing that is called invalid state. Invalid state of the memory element. Okay, so if A, B, my 1, 1, I have got here Q and Q bar is called invalid state. Okay, so these are the 4 states I have got for the memory element. What are those 4 states? One is previous state, reset state, set state, and invalid state. Now what I am going to do, I am going to take both all the 4 cases and I construct this truth table for the particular logic circuit. So what is the truth table? But see here. So I would have A, B, and my Q and Q bar. So here what I got, if A, B, 0, 0, I have got here previous value. If 0, 1, I have made Q to 0. This is 1. This is called reset state. Next 1, 0, Q is 1, Q bar is 0. This is called set state. Next 1, 1 is called 1 and 1, it's called invalid state. Okay, so this is the memory operation where all my desired values has been stored in my memory element. So in this state I have got 0 to be stored, in this state 1 to be stored, in this state previous value of my output to be stored. Okay, do you all understand? So this basic logic circuit has all the desired values to be stored for me. Okay, now I have got one extra invalid state over here. How to eradicate this invalid state, I will tell you later. Okay. So do you all understand? If there is any doubt, tell me. So if there is no doubt, I'll move to the next part. Is called flip flop. Flip flop is called basic memory element. It's a basic memory element. Okay, so before going to start the flip flop, I am going to tell you one important concept here. What is the important concept? The clock pulse. Clock pulse. What is clock pulse? The controlling parameter of the memory element. Controlling parameter. So what is the controlling parameter? What I have to control over here mainly? I have to control over here how much time I want to store the previous value, how much time I want to store the 0, how much time I want to store the 1. Who will control that? mainly the clock pulse will control that. Okay, whatever I have designed earlier the circuit, if I can introduce a clock pulse along with this, that will become my flip flop. So flip flop is nothing else, clock driven memory element. Okay, where the clocking parameter actually controls the storing power. Okay, do you all understand, students? So now the question is, what is clock pulse? Do I'll just give you a glimpse about the clock pulse. You have already studied it. Clock pulse is nothing else the square waves. Am I correct, students? You have already studied the square wave generators, how to generate the square wave, the 555 timer circuit. With the help of that we can able to generate. If you have not studied, that is there in your course. I think I have actually seen that course in the third semester. Okay, this is your third semester. I think you will be studying this, don't worry. This is called square waves. Square waves means this is called clock means this is your time. Okay, and this is called t off of the clock. This is called t on of the clock. Okay, this is 0, this is 1. Okay, this t off plus t on is called total time period of the clock. Now one important concept I'll tell you over here again, that is what is called duty cycle. The duty cycle of the clock is nothing else, t on divided by t on plus t off. Okay, so if it has exact t on and t off, it has duty cycle of 50%. Okay, do you all understand, students? The clock pulse will tell about the flip-flop controlling parameter. Okay, so I will more discuss about the clock pulse later on, don't worry. Just you just understand here that I'm going to control my desired value to be stored in the memory element with the help of this clock pulse. Okay, this is called CLK clock. Okay, do you all understand or any doubt in this? If there is no doubt, I'll move to the next part. So what is the next part? So mainly the types of flip-flops. So first question is, what is flip-flop? Flip-flop is a basic memory element. It is going to store 1-bit binary data. Okay, 1-bit desired binary data, and it will be controlled through clock driven, and it is the clock is the controlling parameter. Okay. So now types of flip-flop. What are the flip-flops are there? The first one is SR flip-flop. It's also called as set reset flip-flop. Very important, students. Surely some questions will come. Minimum 15 marks will come from this flip-flop chapter. Okay. If you are not understanding, it's very waste for you. You cannot get good mark in the exam. So minimum 15 mark. Okay. Remember. Next, JK flip-flop. Next, MSJK flip-flop. Next, D flip-flop. Okay. D flip-flop is also called delay flip-flop. Next, T flip-flop. T flip-flop is also called toggle flip-flop. Okay. Next, user defined flip-flop. So you are going to study all these things. This is very important for PSU exams, and apart from that, these are all very important for your main exams as well as your mid exam. Okay, do you all understand? This I will just teach you because this is very important for PSU and GATE exams. Okay. Do you all understand? So there are how many flip-flops? Around 6 flip-flops: SR flip-flop, JK flip-flop, MSGK flip-flop, D flip-flop, T flip-flop. Okay. So for all these flip-flops, you are going to study what? You are going to study these 7 things. What are those 7 things? First one is, you have to study the logic symbol of the flip-flop. Next, you have to go for the logic design of the flip-flop. Next, you have to go for the truth table of the flip-flop. Next, you have to study the characteristic table of the flip-flop. Okay. Next, you have to study the characteristic equation of the flip-flop. Okay. Next, you have to study the state diagram. Next, you have to study the excitation table. So how many you have to content you have to study for a single flip-flop? Logic symbol, logic design, truth table, characteristic equation, state diagram, excitation table. Okay. So we'll start one by one from the first flip-flop. What is our first basic flip-flop? Basic flip-flop is your SR flip-flop, which is also called what? Set, reset flip-flop. Okay. So we are going to study about it now. So the thing is here, first I have told you what are the things you have to study, all the 7 things. What are those? First, this is first flip flop. First thing is logic symbol of the SR flip flop. Okay, what is your logic symbol? Just see here what I am doing. So very simple, SR flip flop, it having S and R two inputs. Okay, and I have told you clock is the controlling parameter and two outputs Q and Q bar. So this is called your SR flip-flop. Okay, this is the logic symbol of your SR flip-flop. Very simple. Okay, next you have to know about the logic design. So logic design is what I have just discussed with you. The thing, the logic design, I have just discussed with you how the desired value is stored as a set and reset. Okay, so if what is the logic design? Logic design is very simple. So this is the way I have already discussed with you this analysis. It you can also see that with this circuit I can able to store the 0 and 1 and the previous value. Okay, apart from this, one extra thing I am going to add over here, that is actually clock, which is controlling parameter. And I have given there A and B. Here I am just giving S and R, nothing else. Okay, and this is Q and Q bar. Okay, here extra thing I have given here clock. Clock will control the storing parameter, whether it will go for previous state or set state or reset state. Who will tell? The clock will decide how much time it will hold that particular things. Okay, so now after this logic design, I have already constructed for you AB. For AB, what is my truth table? I have already told you there will be little modification over here because I have introduced clock pulse over here, because clock is the controlling parameter. Now you can see if clock equal to 0, okay, if you are not giving clock over here, clock equal to 0, then what happen? Whatever may be your S and R input, it will actually store the previous value. Okay, it will not going to change anything for me. Okay, now I started giving clock pulse here. So if clock pulse is 1, S and R 0 0, what we have got for case 1 student? If A B 0 0, I have got the previous value. I have assumed here initially 0 and 1, so I have got next state is also 0 1, so that I can say that. Okay, now clock pulse is present 0 and 1. What it will do? It will just reset. Or you can see this R is 1. R is 1 means reset equal to 1. So it will just reset my flip-flop output. Whatever may be my previous output, whatever may be my assumption, it will just reset my output to 0. So this is called reset state of my SR flip-flop. Okay, next clock is present 1 0. What it will do? It will just set S equal to 1. So it will just set my output. So this is called set state of my flip-flop. Now clock is present 1 1. If 1 1, what we have got students? 1 1, which is called invalid state of my SR flip-flop. All of you understand students? Very simple. The truth table is very easy. Okay, so this is my truth table. Now fourth part. After that, what you have to do? You have to do the characteristic table. So what is characteristic table? If I ask you what is your character, how it will be decided? How you have worked, how you are hard worker or not, are you obeying your parents or not, are you doing your work in proper time or not, are you going for the classes properly or not, are you listening to the teacher or not? This actually decides your characters. Okay, so what actually character of a flip-flop? The character of the flip-flop is nothing else. Understand here the state of the flip-flop. So before character, I will tell you one important concept. So what is that? The state of the flip-flop before applying clock pulse. The state of the flip-flop before applying clock pulse. So there are two state students for applying clock pulse. So you have not applied the clock pulse before that what is called, what is that state is called as present state, present state, which is denoted by Qn. Okay, please try to understand. State of the flip-flop before applying clock pulse is called present state. Now, state of the flip-flop after applying clock pulse. State of the flip-flop after applying clock pulse. Applying clock pulse is called what? Is called as next state of the flip-flop. Next state. What is next state? Qn plus 1. Okay. Before application of the clock pulse, it has present state. The flip-flop will be in the present state. After application of the clock pulse, the flip-flop will go to the next state. What the characteristic table will tell? The characteristic table will tell here that how the state transition will happen from present state to the next state with the application of the flip-flop inputs. Okay, here what are the flip-flop inputs? S and R is the flip-flop inputs. With the help, if I apply certain flip-flop inputs over here, maybe S0, R equal 0, S equal 0, R equal 1, S equal 1, R equal 0, S equal 1, R equal 1, how the state transition from the present state to the next state will happen. How this transition will happen? If I apply certain clock pulse, if I apply clock pulse, then it will move, flip-flop state will move to the next state. So what characteristic table will decide? The characteristic table will decide how the state transition from Qn to Qn plus 1 with the presence of flip-flop inputs. Are you understanding, students? So that actually tells the character of the flip-flop, any flip-flop. So here Qn, S and R are my, if you understand this, then only it will be easy, students. So see here, before drawing this, as you know that there are three inputs, so three variables, so obviously 8 different combinations possible. 0 0 1, 0 1 0, 0 1 1, 1 0 0, 1 0 1, 1 1 0, 1 1 1. So now how to find out Qn plus 1? So this is called what, students? This is called present state. Okay, what is present state? Before application of the clock pulse. Before clock pulse. Now, after application of the clock pulse, it's called next state. Okay, do you all understand, students? Now, how to find out this next state? Okay, so now you know that what is my truth table tells? My truth table tells that if S and R 0 0, what it will just store? It will store the previous value. So what is the previous value? Presently now, what is actually my output? Presently my output is what? 0. Are you understanding? Presently my output is 0. If I give S and R 0 0, it will just copy the previous value to 0. Are you all understanding? Because I have already know that S R, this is my output Q bar. If it is 0 0, previous value. If it is 0 1, it is reset. If it is 1 0, it is set. If it is 1 1, invalid. Okay, so we know this. This is my truth table. We know this. According to this, now next state I am just deciding. So here you can see 0 1. What it will do? It will not check what is the previous value actually. What is the present state actually? It will just reset my flip-flop output. So this is called reset. This is called previous value. Are you understanding? Now 1 0. 1 0 means it just set my, it will not check what is my previous present value and all. It will just set my output. That is called set. Now 1 1. 1 1 means it will not check what is my present state and all. It will just make the invalid output. Invalid output means don't care, which is called invalid. Are you understanding, students? Very important. Just I am deriving from the truth table, nothing else. Whatever my present state, what would be my next state? I am just checking it, nothing else. Okay, 0 0. Again, it will just present state. Okay, 0 1. It will just reset. 1 0. It will just set. 1 1. Don't care. Are you all understand? So this is my characteristic table of a flip flop. Okay. If you understand this, you can able to understand next part. Else, very tough for you. Please let me know, did you understand the characteristic table or not? Okay. If you understand, we'll move to the next part, characteristic equation. So what is characteristic equation? How to find out this characteristic equation? Now we know that characteristic output is like this. If you can form a SOP form of it, then I can have a equation. It's in the form of equation. So obviously this is a three variable. So obviously three variable KMF will be give me this characteristic equation if I solve it. So my three variables are here. What are those my three variables here? QM, S, R. So this is my S bar R bar, S bar R, S R, S R bar. This is my QN bar and QN. As I know that my place values 0, 1, 2, 3, 4, 5, 6, 7. So how is my place values here? This is my M0, M1, M2, M3, M4, M5, M6, M7. Okay, so you can see 0, 0, 1 don't care. So 0, 0, 1 don't care. Next 1, 0, 1 don't care. 1, 0, 1 don't care. Now what I will do, I'll just group it. What is possible here? Next we'll have a page. Okay, from this what I have got? From this grouping I have got S. From this grouping I have got R, Q, N. Am I correct? No, R bar Q, N. Okay, so what is my characteristic equation of the SR flip flop? Qn plus 1 is nothing else, S R bar Qn. Okay, so this is called characteristic equation of SR flip flop. Okay, all of you understand, students? Very important. Now, if there is no doubt, we'll go to the next part, sixth part of the flip flop, which is called state diagram. Before starting, I'm going to tell you one important concept regarding state diagram. What is state diagram? State diagram is nothing else, just the representation of state transition. Representation of state transition. Representation of state transition. What is state transition mainly? State transition is nothing else. How flip-flop is changing from a state from present state to next state. Okay, how flip-flop is changing its state from present state to next state is derived from this state diagram. Okay, so what is present state? I have told you Qn plus Qn. What is next state? Qn plus 1. Okay, do you all understand or any doubts, friends? Qn plus 1 is next state. Okay, how this flip-flop is changing its state from Qn to Qn plus 1, I am going to say here in the state diagram. Okay, so before starting that, some few rules I am going to tell you to design state diagram. First one is, one flip-flop has always two possible states. One flip-flop has always two possible states. What are those states? 0 and 1. State diagram, the states of the state diagram. Okay, state diagram is represented with circle, is represented with circles. Okay, so do you all understand what is that? How many states I have told you? First of all, 0 and 1. Okay, do you all understand the states of the state diagram? This is one state, this is another state of the flip-flop is represented with circle. Okay, these are called 0 and are called states. Are you understanding here what is characteristic table? The states are what? Present state is either 0 or 1. Am I correct? Next state is also either 0 or 1. Maybe don't care. Don't care is what? Don't care is nothing else, either 0 or 1. Am I correct, students? So what do you understand from this? A flip-flop must have only two states, nothing else, and the states are represented with circles. Next. Okay, next one is what? State transition. State transition. State transition is are going to be represented with arrow marks. Arrow marks. Okay, which indicates the origin of the arrow mark stores. So the state transition means from 0 to 1 state transition, let's say like this, like this, like this, like this. There may be this possible four state transitions. Am I correct? Eh, are you understanding? It may go from 0 to 0, it may go from 1 to 1, it may go from 0 to 1, or it may go from 1 to 0. So these are the actually state transitions. State transitions are represented with arrow marks. From the arrow mark, what you understand? It has 2 points. One is origin and another one is end point. Origin is actually the present state of the flip-flop. End point is called the next state of the flip-flop. Any doubt, please let me know. This present state is what I have told, Q1 before application of the clock pulse. Okay, before application of the clock pulse, and next state is Q1 plus 1 after application of the clock pulse. Any doubt, please let me know. If not, I'll go for the next part for the state diagram design. So see here, SR flip-flop state diagram. So very important 2 mark question also come, like design SR flip-flop state diagram, design JK flip-flop state diagram, design T flip-flop state diagram, design D flip-flop state, anything can come up. Okay. SR flip-flop state diagram I'm just designing. So two things you understand from here. One is a flip-flop has two possible states, either 0 and 1, and the states are represented inside the circle, and transitions are represented with the arrow mark. Starting from origin to end, origin will be present state, end will be next state. Any doubt? If there is no doubt, we'll move next. So SR flip-flop state diagram, it has two states, I have told you. Okay, so the state transition is from, let's say, 0 to 0, means present state is 0, next state is also 0, let's say. Okay, so now tell me what is S and R value during that time. So see here, how to find out state diagram. If you can able to draw the characteristic table, then only you can able to find out the state diagram. Okay, so see here, what is my state transition? State transition from 0 to 0. So where is 0 to 0 state transition happening? In this case, see here, present state is 0, next state is also 0. This is the case where 0 to 0 transition. Any other place? Yes, this is also the case. There will be 0 to 0 state transition. In present state is 0, next state is also 0. Present state is 0, next state is 0. At that time, what is my S and R value, students? My S and R value is 0 0 0 1. Just I am going to put over here. Okay, 0 0 0 1. Now tell me, S value is fixed, but R value is one time it's 0, one time is 1. Can I write down this is 0 and don't care? Do you all understand? Because R value is not fixed. It is sometimes 0, sometimes 1. So I have made it to 0, don't care. Okay. Now let's say my state transition from 0 to 1. Tell me in the characteristic table, where is state transition 0 to 1? 0 to 1 state transition. Can I say this one? 0 to 1 state transition? Yes. Okay. Any other place 0 to 1 state transition? No. Only for S and R value 1 0, we have 0 to 1 state transition. So my S and R value here, what is that? My SR value here is 1 0. All of you understand here how I am doing? Just I am representing from the characteristic table how the state transition I am writing with the presence of the flip-flop inputs, nothing else. Now let's say my state transition is from 1 to 1. Okay, now tell me in the characteristic table state transition 1 to 1 where it is. So 1 to 1, can it be here? Yes, state transition from 1 to 1. And can it be here? Yes, transition from 1 to 1. These two cases. So at that time, what is my SR value? SR value 0 0 1 0. Am I correct? My SR value is here 0 0 1 0. So here S is fluctuating. So I can write down here don't care 0. Am I correct, students? Very simple. Next, my state transition from 1 to 0. If my state transition is from 1 to 0, where is the case 1 to 0? Here. You can see in this case 1 to 0. Okay. Any other place? No. Only this is the case where state transition from 1 to 0. At that time, what is my SR? 0 and 1. My SR is 0 and 1. Okay, so this is my state diagram, students. How I'm just doing it neatly over here for you. First of all, I have told you a flip-flop has two states and states are encircled and state transition is from 0 to 0. At that time, what is my SR? 0, don't care. I have already find out here. My SR is 0, don't care. State transition 0 to 0 means present state is 0, next state is also 0. State transition from 0 to 1. At that time, what is my SR? My SR is 1 0. State transition from 1 to 1. What is my SR? My SR is don't care 0. State transition from 1 to 0. What is my SR? 0 and 1. So do you all understand? This is my state diagram of. So what is actually state diagram tells? State diagram tells how the state transition with the presence of SR inputs, nothing else. All of you understand? Now the last part actually. The last part is seventh part. If you understand up to this, next only you will understand the excitation table. So now what is excitation table? Just 2 minutes, students. Excitation table shows the different possible state transition in presence of the flip-flop input. So this state diagram to table formation is excitation table, nothing else. What actually excitation table will tell? It shows the different possible state transition, different possible state transition with the help of state transition in presence of the flip-flop inputs. So do you all understand? So what it actually tells? The excitation table tells how the state transition in presence of the SR flip-flop. So if I can represent this complete SR flip-flop state diagram into the table, that is nothing else my excitation table. Do you all understand? So all are interrelated, students. So in the excitation table, what are the input of the excitation table? Input of the excitation table are Qn plus 1, means present state and next state. And what is the output of the excitation table? Output of the excitation is flip-flop inputs. So what is flip-flop inputs here? S and R. So now I can derive this excitation table here. Qn plus 1, S and R. So Qn plus 1 0 0 0 1 1 0 and 1 1. So if state transition from 0 to 0, then what is my SR, students? I have already drawn in the state diagram. What is my SR? If state transition from 0 to 0, my SR is 0 don't care. So I'll just write down here 0 don't care. State transition from 0 to 1, what is my SR? 1 0. Okay. State transition from 1 to 0, 0 1. State transition from 1 to 1, what is my SR? Don't care 0. Over. Do you all understand, students? Very important. So if you understand this, then only you can able to understand next flip flop. So what is my suggestion, students? You guys has to see the video and again practice at home.